thank you for that introduction. Get into my words. On data centers, more specifically trying to understand traffic charges data centers, trying to find ways to actually control traffic. And this is 3 years old. A lot of things in data centers, and I was trying to talk about how, despite the change, a lot of things also have still important. So kind of starting off, I think we're all familiar with the fact that data centers are crucial. They're extremely important. They're used to host a lot of services that we actually use. So as internal users, they use to host line of business applications. If you want to go on vacation, you go to your company website, fill out a bunch of forms, and all goes to a data center. And then they're also used to host services for external users. So basically, you could think of your Flickr, you could think of your Yahoo Mail, you have Yahoo Chat. Everything's all hosted on data centers. So basically, a lot of things are hosted on data centers. And performance of these data centers is actually quite important. I don't actually need to talk about why it's important. Earlier on, PPSN talked about the importance of performance for end users. So, kind of, the first question then becomes, what does a data center look like? Oh, I guess what did data centers look like 3 years ago? So basically, starting at the bottom, you have a bunch of servers, and if you're a virtual service, it goes all of the services we run, and they're connected together by a set of edge or top-of-rack switches. This essentially does bring connectivity to the servers. And then going one level up, you have the aggregation, which basically just brings together various parts of the data centers and gets connectivity from the east to the west side of the data center. And at the very top, you have the core, which is what allows the data centers itself to connect to the outside world, basically providing connectivity from application servers to wide area network and between data centers and other data centers. So in terms of our actual study, we actually covered a large array of data centers, and there was a huge difference in terms of size and usage. So basically, you'll see we have some data centers from a couple of universities, we have some data centers from a bunch of private enterprises, and we have some data centers from a huge cloud provider. So this kind of covers the whole range of data centers from small, medium to large. So basically, when we talk about some of our observations, you can see that it's going to span a large array of data center types. And from these data centers, we collected 3 types of data. The first is basically your Snmp data, and what this actually gives you is bytes in and bytes out on individual links. So this tells you how much traffic is being sent, how much traffic is being received, and in this case, it also tells you how much traffic is being lost on the individual links. The only downside is this is averaged over 5-minute intervals. So basically, what you're getting is an average of what's being sent, an average of what's being lost, and an average of what's being received. And to complement this, we had some low-level information. So basically, we had packet traces, which tell you essentially what bytes are being sent on the wire itself. So now you can basically say, I had averages over 5 minutes. Can I actually zoom down and look at everything instantaneously as traffic is being sent? So we had port spans from a couple of data centers, and that just gives you a packet dump. And then the last thing we had was just like a topology, which tells you the roles of the various devices. Now that you have a topology, you can figure out, right, this is an edge device, this is an aggregation device, this is a core device. This is kind of how traffic is kind of maybe flowing through this data center. So basically, the topology is kind of very good in terms of trying to put all the data that you have together. And trying to understand kind of where we collected the port spans from. So the port spans were from the uplinks from the edge of rack to the aggregation. So what you're actually seeing is the traffic that's leaving the rack and imposing itself on the data center, interconnect itself. And this is going to become important towards the second half of the talk when we kind of talk about what the link utilizations themselves look like. So in terms of an outline for this talk, we'll start at the bottom, talk about the packet traces, look at the micro level properties of data center, basically what are the traffic patterns, what kind of traffic should we try to model if we want to test out architectures. Then we'll go up and look at the macro level and basically try and understand what does loss look like, what does utilization look like, what does predictability of traffic look like. Basically, if you're trying to come up with traffic engineering techniques, these are a couple of things you kind of want to know and keep in mind. And then finally, we'll talk very briefly about what you could do with some of the observations we have. So I'll show you a system that we built based on the observations. And finally, we'll have some retrospective remarks of, the world has changed in the last 2.5 years. How does this impact a lot of what we found? And what kind of new things do we expect to show up? So starting with the microanalysis, we basically, as I said earlier, we collected packet traces. And so we're going to essentially use a Bro identifier, which is a tool out of Berkeley that looks at packet traces and tries to determine what set of applications they're running. And we've augmented the Bro to basically identify new applications that have come out within the last 5 years. But it's basically doing some port identification to figure out what applications map to packets in the traces. And so the graph here just basically has the private data centers and the university data centers. It has each bar tells you how much percent of traffic, and it's color-coded by the actual applications. And the main takeaways is in terms of these private data centers, educational data centers, what you actually end up seeing is a lot of HTTP, HTTPS, and if you think back, it's all of your line of business applications. Those are all kind of run off of web servers. And then you'll also notice in the universities there's a large amount of file system traffic. So basically this is, in the private you notice HTTPS, HTTP, do I have a pointer? Okay. Oh yeah. So then you notice basically when you start to look at some of the applications, you notice some Snmp. You should also notice some LDAP over here in the private. So basically you're noticing file system, a discrete file system, you notice a bunch of web services. And then in terms of the clouds, what we basically have there are two that are specifically running MapReduce applications. It's actually running Cosmos. And then 3 that are running MSN and Mail and a couple of other properties. So basically now we've kind of understood what kind of applications are being run. And next thing we'll basically try to look at is basically what does the traffic itself look like and why is this important? Kind of going back to the idea that data centers are changing and we have to come up with new techniques for these data centers. And then one step further, we have to evaluate these techniques. And to evaluate these techniques, you need to come up with packet generators, you need to come up with flow generators, you basically need to come up with traffic generators for data centers. And to be able to come up with realistic ones, you need to understand what the actual traffic within data centers look like right now. It's kind of like a chicken and an egg problem. So basically, we're going to look at, start by looking at packet traces, a simple time series, try to understand what does traffic look like on the wire. And the one observation we had when we actually looked at our regular time series was basically some kind of on and off going on. And so we essentially end up binning the traffic and trying to understand does the on and off hold across several different types of bins. And we end up actually saying the answer is going to be yes, because we tried a couple of bins. Here I present 2 bins, 10 milliseconds, 15 milliseconds and 100 millisecond bins. And the main idea here is just basically, despite how much you bin it, on and off still kind of holds. And so we basically, going from the fact that now we know traffic's on and off, next question we had was, what are the arrival patterns in the on period? What is the distribution for the off period? What's the distribution for the on period? And these are things you use to determine basically, should I be using Poisson, should I be using Pareto, should I be using something that's different from those two? When I'm trying to understand the long tail, which is the right distribution to understand the long tail of latency? Which is the right distribution to understand the long tail latency? And before I kind of jump into the distribution itself, I just kind of want to go back and give you a brief primer. So why are we seeing bursts of packets within these networks? And it's kind of very intuitive, and if you think about it, we've done a lot of things to optimize the network. So in terms of TCP, you think TCP, I send a packet, it sends me an ACK, I send another packet, it sends me an ACK. And in reality, we have an optimization where I send a couple of packets, then I get an ACK, and now the ACK actually ACKs a bunch of packets. Now, next thing the server is going to do is actually going to send you a train back. So now we have this optimization, we have delayed ACK optimization, where basically we're starting to introduce burst just because we optimize the network itself. So here's one first thing where, as an optimization to improve the network, we're now introducing burst into the network, which is actually kind of bad for the data center. Here's another optimization we have. So now you think, I send a packet into the network, it goes in. But in reality, because there's an interrupt between the kernel and the network card, it actually takes a huge amount of processing if you want to actually process every interrupt for every packet. So now you end up saying, all right, I'm going to batch a couple of packets, and when I have some number of packets, then I'm actually going to service an interrupt for them and send them into the network. So now you're seeing more batching, and now you're basically seeing more bursts of packets. So basically, the burst, while initially looks a little surprising, you expect them to be spaced out, we actually have a couple of optimizations that we've set up within the network and within the operating system itself to make things a whole lot better. But the end result ends up being burst into the network, which is basically things that get lost. They get lost on the wire itself. So this is just kind of give you an intuition for why bursts exist. So now kind of going back to the traffic itself. So if you want to figure out what kind of distributions we need, we basically have to fit the distributions, fit the on-model, fit it off, and fit into arrival time. So we're going to do this using MATLAB. MATLAB has a very nice function that allows you to fit curves to various distributions. So we basically did the fit, and the main high-level takeaway is basically all of these end up fitting heavy-tail distributions. Some of them fit log normal, some of them end up fitting Weibull. And I guess it doesn't actually matter which heavy-tail distribution we fit, just the fact that we fit a heavy-tail distribution. And the reason why this is important is because prior to this, we were all saying we already have good models for wide area network. These models are basically Pareto models, and we've done a lot of work for the last 20 years trying to figure out what the right set of Pareto models we should use to model things and traffic for data center experiment. I'm sorry, for wide area network experiments. So now moving to data centers, we just basically reuse the tool. It's kind of like how someone said earlier, a lot of the tools for the mobile and just things we've already used in the wire moved over. So we have this really awesome habit of reusing tools we've had in the past. But in the case of data centers, this is not actually that good of a habit because now the traffic itself has changed, and if we're actually using these old models, it's actually a little bad. And to understand why it's bad, let's go back to the fact that these are two fundamentally different distributions. While they look the same in terms of the mean, if you actually look at the tail, there's a huge difference between the Pareto and these heavy tail distribution. And this just basically, the tail is actually much longer for these heavy tail distributions. And this is especially important if everyone tries to focus on the 99 percentile in terms of trying to model how well you're going to do in terms of modeling escalate violations. So if you use the wrong distribution, you're going to end up thinking everything is okay, there'll be fewer violations, and I'm good to go. But then reality hits in, and now you have a whole lot more violations, and that's just because you've essentially tested your techniques and everything using the wrong model. So basically, this is one of the reasons why it's kind of right, and it's good to use the right set of models. So that kind of covers looking at the packet traces and trying to understand what kind of models we can extract from packet traces. The next thing we're going to look at is basically what happens in the network itself. So we've seen what the packet traces are, what the packet looks like going into the network. Now, how does the packet traces, how the packet themselves impact the network? So first question is, we know some traffic leaves the rack, but how much of this traffic actually goes onto the network? How much is between application servers within the rack? So basically, this is kind of a question of, if we have a lot of applications that are rack aware and rack local, how effective are they? So the main idea right now is we want to figure out how much traffic leaves the rack. And since we don't have some kind of a measurement that just tells us this is what leaves the rack, we have to do some very simple math to figure this out. And I'm going to say it's very simple math because it's literally very simple math. So to figure out what's to figure out how much traffic is staying in the rack versus leaving the rack, we go through the idea that first, we know how much traffic is leaving or going on the uplink. So basically, the Snmp information tells you how much traffic is going up here. So we can basically figure out the extra rack traffic, all the traffic leaving the edge. And then we have Snmp that tells us how much traffic is being sent up by the servers. So if we say the amount of traffic that stays in here is traffic going up minus traffic going up here, then we can say the intra-rack traffic is just the sum of the server uplinks minus the edge uplinks. So it's kind of like really, really simple math. But this gives us an idea of how much traffic the servers send onto their links that actually leave versus actually stays within the rack itself. There are some minor exceptions, like what happens when there's multicast, what happens when there are VLANs. These kind of make numbers a little funny, but I'm going to ignore that for now, and for the rest of this talk, actually. So here we have a graph that just has a couple of the data centers on the x-axis, and the y-axis just basically has the percent of traffic, and the blue is how much traffic is staying within the rack and how much traffic is leaving the rack. So the big idea is, if we look at the left side, if we look at the right side, you will notice that in all of the cloud data centers, a huge amount of traffic stays within. And this kind of agrees with a lot of what we think about when we think of MapReduce and we think of cloud applications where it's all local and all rack aware. So you're trying to keep and point things together. And then if you look at the universities and small private data centers, it's a bit more spread out. And this is because unlike the cloud where there's a huge focus on putting things together because these are much, much bigger. So if you remember, the cloud data centers are about 500 devices. And the smaller ones where these are about 100 to maybe 50 switches. So there isn't a huge importance just on trying to make things local. And also because these guys actually have significantly less traffic. So it's okay to waste network resources. Here, network resources are very crucial. So you're basically trying to keep things rack aware. So a couple of interesting questions we might have now that we know that a lot of traffic stays in the cloud. We know a lot of traffic stays within the rack, and only a small amount leaves the rack and goes over the and goes over the interconnect. One question is this traffic predictable? So it's 25% of traffic. Can we say this is predictable? If it's predictable, we can use a lot of nice and cool techniques. Next question is how much. So if it's only 25% that leaves, how much of the network is actually utilized? Are we just wasting a lot of resources? And finally, if there are packet loss, where does this exist within the hierarchy? So we'll start by looking at what is predictable. And the idea is basically, we're going to group things together and say traffic from one edge to another edge is predictable if you look at a bunch of time series, in this case, 100 millisecond bins. If you look at a bunch of these bins, you see only like a 5% variation in terms of the amount of bytes sent. So basically, it's predictable if bytes sent from one time series to another time series hasn't deviated by much. So here's a CDF that just basically has on the y-axis it has percent of traffic that's stable, and the x-axis on the and the x-axis is basically has percent of traffic that's stable, and the y-axis just has the CDF. And the main idea is basically we're going to look at the medians for all of the CDFs I present. Here in the median case, you see that at most 23% of traffic is predictable. So if you start to think about this, what this means is there isn't a lot that's predictable within these data centers. So if you try to do something that's traffic engineering and you want to focus on the fact that you can predict things, it's not going to work out. So you need to actually gear yourself for the fact that a lot of traffic is unpredictable. So this is like the one observation. And then another question I might have is, well, I know something's predictable. How long is it predictable for? So if we focus on just the part that's predictable, we end up finding out that even in the best case, it's only predictable for about 2.5, 2.6 seconds. So if you were to try and react to predictability, you'd have to react in a very, very short time period. So you basically don't have a lot to work with. And even the small amount that you have to work with, you don't have a long amount of time or large amount of time to actually do anything realistic with it. So this kind of answers the question of what's predictable and how long. Nothing, and not for a long time. We'll come back to this in a couple of slides. But let's kind of go back and think about utilization. So how are the links utilized? This graph just basically, it's another CDF again, and here there are 3 different lines. And the lines have the utilization for links in the edge, the aggregation, and the core layers. And the main high-level takeaway is the core is higher utilized than the edge or the aggregation. And this is just basically, if you think about it, I showed you earlier, let's go back a few slides. This is what a network looks like. As you go up, there are fewer and fewer devices. So it only makes sense that as you go up, the traffic that does actually get onto the network is getting onto fewer and fewer links. So utilization is essentially higher. Utilization is essentially higher. And then the edge has a slightly higher utilization than the aggregation, just because the edge is actually just 1 gigabit, whereas the aggregation is 10 gigabits. So even though the traffic, there might be higher number of bits per aggregation link, the aggregation links themselves are much fatter than the edge links. So this just basically kind of giving you an idea that the core is the most utilized. The next question is, an obvious thing from this is, if the core is the most utilized, I expect the core to have the most losses. So you want to think loss is correlated to utilization. And so if you actually look at the losses, there's somewhat of a reverse trend. The aggregation has the most loss rates, the edge has the second most loss rates, and the core has the least amount of loss. And just trying to go back and think about the edge and the aggregation. We talked about how things are very bursty within the data center. When things are bursty, the first pipe they hit is going to be the edge pipe. The edge pipe is going to restrict the bus, restrict the burst, because essentially, if I'm trying to send a whole flood of packets and there's a 1 gigabit link, only 1 gig is going to go out. So as you kind of go up the hierarchy, a lot of the bursts are getting like eliminated by just packet losses at different layers within stack. So now let's kind of talk about how we can try and use some of these observations to do something. So the last couple of slides we talked about, traffic is bursty, loss happens. It's kind of predictable, so we can technically adapt to it, but there's only a small amount of traffic that's predictable. And finally, it's predictable for only a very short amount of time, so if we want to react, we must react very, very quickly. And this kind of led us to this idea that, well, can we come up with a system that takes advantage of partial predictability and tries to improve the performance within data centers? And our solution to this was a system called MicroTE. And on a high level, MicroTE has 3 basic components. The monitoring component basically tries to aggregate a traffic matrix of the whole network. And in the ideal case, you would have the switches figuring this out, but that doesn't actually scale. So we end up having the end host try to piece together the traffic matrix. And then to send this to a network controller, the network controller being a central entity and a brain for the whole network, puts this together and tries to figure out what parts of the traffic is predictable, sends this to a routing component that says, all right, for the predictable traffic, I'm going to do something special. For the unpredictable traffic, I'm just going to throw my hands in the air and hope something works out. So this is essentially high-level overview of the 3 components. I'm not actually going to go into the details for them, but in terms of questions about the architecture, some interesting questions we had to deal with was basically, how can I effectively gather network state? I need to gather this information and react within 1 second. So how can I do this effectively? How can I determine predictable traffic? And how can I calculate new routes and install them within the network in a very efficient manner? And last question, I guess, is how to install it within an efficient manner. In this talk, we'll briefly talk about the middle 2. And essentially, high level, the routing component gets this global view, so it knows what's going on in the whole network. It has a historical archive that has global views from the last couple of 0.1 seconds. And then it basically looks over the traffic matrix, uses an estimated moving average to determine what parts are predictable, and then basically tries to pin the predictable traffic to a certain set of routes. Then it basically says, well, for everything else that's unpredictable, I'm going to use some form of weighted Snmp, discounting the fact that for some of my link capacity I've already assigned to the predictable traffic. Then it installs routes. Basically, we try and leverage OpenFlow to install the routes. And in terms of how do you figure out, or how do you create routes for predictable traffic, we had 2 approaches. The first is NLP formulation, where you basically look at the traffic that's predictable, and you only look at the traffic that's predictable, and you try and pin them to certain routes. The idea is you want to minimize the maximum utilization, and this is kind of going back to how we always create or develop traffic engineering techniques. You try and minimize the utilization, hoping that this reduces overall reduces the chances of congestion of any one link. And in terms of constraints, we basically have flow conservation, capacity constraints, and we try to restrict ourselves to 4 equal length paths. And then we have a heuristic version to basically try and scale to bigger data centers, because it turns out the LP doesn't scale that well. So in terms of the implementation, we've implemented this using OpenFlow, and we added a kernel patch to like each of the Linux modules we had. And we basically wrote a lot of this stuff in C++. It was a lot of fun on that. And then we had a bunch of interesting questions. Basically, how does our approach compare to like the optimal technique? How does our approach perform under varying levels of predictability? So we showed that within one of the cloud data centers, we had about 27% predictability, but within the universities, we had more predictability than so basically, we've shown you what the pessimistic case was, and we wanted to understand how we perform under much better situations. And then the question was basically, how well can we scale? We have this idea that we want to get things done within 1 second. What's the largest approach we can scale to? And finally, what sorts of overheads do we impose on the network? And we'll just kind of focus on the first question, how well do we compare? I can talk about the other questions offline. So to basically evaluate this technique, we essentially created a simulator the simulator takes us input a traffic matrix, so we have all of this data already around. A topology, we also have that data, abundant amount of that data. And then we take a traffic engineering technique. So we have our super awesome MicroTE technique. We have the default, which is ECMP, equal cost multipath. And then we created this optimal technique that basically uses an oracle. It looks ahead into the future, figures out what kind of traffic you're going to send, and preemptively creates the optimal routes for that set of traffic. So this is the best we can ever do. And then we use the traces from one of the cloud data centers. We actually use several different traces, but we're only going to talk about the traces from the cloud data center. And once again, this is the most pessimistic trace we had. So here we have another CDF. I'm a huge fan of CDFs. Here's another CDF, and there are 3 graphs here. There's an ECMP, there's MicroTE, and there's optimal. And essentially, the main high-level takeaways: we're better than ECMP. I feel like every technique shows you better than ECMP. If you're not, you failed somewhere. But we're still worse than optimal, and we're worse than optimal by 1 to 5%. This is because we're always trying to predict what we think is going to be stable traffic, and it turns out a lot of times, well, not a lot of times, but 1 to 5% of the times we're actually kind of wrong on what we think is going to be predictable traffic. And so when we try to set up routes for them, the routes end up being superfluous routes. So now we can have this retrospective remarks section. So we all know everyone's working on coming up with cloud-style data centers. I think Bing has already created or has a couple of nano presentations about their cloud-style data centers. So we know they're deploying them. We all think Google might also be deploying such data centers. And the main difference between this canonical data center and a cloud-style data center is basically now you have a larger bisection bandwidth. So there is 1 gigabit to 10 gigabit links. So now they're 2 huge threads. And in terms of implications for our results, the first result we talked about is basically traffic's bursty. And I'm going to argue this is only going to grow because now that we've gone from 1 to 10 gigabit, we now have to come up with a whole lot more optimizations to basically use the 10 gigabit capacity. So now we have a whole lot more. And in terms of flow characteristics, I think it's still going to be kind of on and off. There might be some difference in terms of what the inter-arrival times in the periods look like, but it's still going to be on and off. And that's just because fundamentally we haven't changed the applications we're running. It's still either MapReduce to MapReduce or a person to a server. So it's still going to have the same kind of patterns. And in terms of utilization, I just basically moving things and spreading things across the whole data center in an attempt to basically become more fault resilient. So the one huge thing that might change is basically utilizations at the core and at the aggregation layer. This will become more evenly spread out across the various links. And essentially, in terms of distilling all the information that I've actually done over, traffic is bursty. A lot of losses actually occur in data centers, and this occurs at the edge, where basically the first amount of burst hits the network. A lot of traffic stays within the rack right now. This is just because a lot of things are rack aware or local aware. And data center traffic is partially predictable, and we've tried to use this predictability to minimize loss. And I want to kind of point out that even within these neo-cloud-style data centers, there's still partial predictability, and there are still people trying to use this partial predictability to actually improve performance within the cloud-style data center. So the fact that what we did was for an old data center doesn't actually eliminate the insight behind this technique, because people are actually applying this insight to current data centers. And I think with that, I'll end the talk and accept questions.
Thanks, Theo.
Thank you.
Any questions?
Hi, so you mentioned that one of the primary reasons for the bursty nature of the traffic was optimizations on TCP and rack switches. So I'm kind of wondering that to see the kind of coordinated burstiness in the traffic, wouldn't it be assuming that all of those hosts are kind of running the algorithm at the same time? I mean, if you expect each host to be running the algorithm, wouldn't you expect the burst to be spaced out over time?
No, so that's actually a very good question. Yeah, I agree. You would expect the burst to be spaced out over time, but the applications themselves are synchronized. So the hosts are not synchronized, but the applications they're running are synchronized. So if you take the 2 main applications that people run, right now, the MapReduce has a lot of barrier phases between communication. So you only use the network when everyone has synchronized to a certain state. So basically, between a map and reduce, we only draw from the map once all the maps are done. So there's an implicit synchronization there. And then if you think about the other set of applications, which are like the 3-tier applications, when I connect to a 3-tier application, I connect to one tier. We all connect to like one tier. And then that tier decides to connect to a bunch of other tiers. So there is some kind of, I'm not sure what the exact word to use, but it's like a chain event in terms of like if I connect to like my web service on the server, then it's going to talk to this other server. So there's going to be like a little cascade. So even though the servers themselves aren't synchronized, the applications are a little synchronized with each other. So that's kind of where some of the synchronization at the edge comes in. If you look at the aggregation, there'll be less of this on off of that, because then it's a bunch of like, it's information from a bunch of different servers, a bunch of different types of applications being intertwined.
Okay, cool. Thanks.
Any other questions? So I have a question for you. I was wondering why you chose to do traffic engineering in millisecond timescales, because at milliseconds you probably want to pace TCP ACKs, or you probably, at second scale, you probably want to do traffic shaping. So did you also explore that option of ACK pacing?
No. So this was the first attempt to try and see what we could do. Mm-hmm. At the end of this, the big insight we got was this is not actually worth it. Because yes, we've improved the NLU and we're closer to like the actual optimal, but the optimal itself, if we go back to that graph, wasn't actually that good. So the end result ends up being a lot of these data centers, at least the cloud ones, are running MapReduce. Why should I focus on just the traffic itself when I can focus on the endpoints themselves? So that was the big takeaway we got from that. And so now we're just not focused on TCP itself, we're just focused on moving the endpoints and changing what the traffic matrix itself looks like.
Okay. I guess we don't have any other questions. So we will